Today's session, we're going to perform a motor starting analysis. The starting motor appears to the system as a small impedance connected to a bus during the period of motor starting. It draws a large current from the system, usually about 6 times the motor rated current, which therefore results voltage drops in the system and inflicts disturbances to the normal operation of the other system loads. Since the motor acceleration torque is dependent on motor terminal voltage, in some cases, the starting motor may not be able to reach its rated speed due to extremely low terminal voltage. This is the reason why we need to perform a motor starting analysis. One of the objectives why we are performing a motor starting study first is to investigate whether the starting motor can be successfully started under the operating conditions. And second, to see if starting the motor will seriously impede the normal operation of other loads in the system. This session, we will conduct only static motor starting. In static motor starting, the starting motors are modeled by the lock rotor impedance during acceleration time, simulating the worst impact on normal operating loads. This method is suitable for checking the effect of motor starting on the system when the dynamic model is not available for starting motors. Anyway, in our next lesson, we will be performing also dynamic motor starting. Okay. The power single line diagram that we are going to use is the same power single line diagram that we used earlier from our previous lesson, the short circuit analysis based on IEC standard. So, this is taken from, as I've mentioned earlier, this power system, the single line diagram is taken from my previous project, the gas oil separation plant project. Okay, so we will going to check which motor that we will be used for our model. Okay, so from this power system, we have two medium voltage motors, 33 kV motors. One is the active or continuously running, and the other one is standby. This motor is a water injection pump motor. Okay, it is rated around 8,500 kilowatt. Okay, so we're going to use the motor which is connected to bus A will be our model motor. Okay, so let's start now running the motor starting, the static. Okay, but before that, okay, since this motor is having the BFD, we're going to update the connection for this BFD, because we will having an error if we're going to start the motors, we're going to run the motor starting and the motor is connected with BFD. Okay, so let's click this button here, rating. Okay, And from here, from the bypass switch status, okay, let's close this one, okay, and close also this one. Meaning, if you are closing this one, you are using the bypass switch. Meaning, the motor will not be using the BFD. Okay? And let's click OK for this. Okay? Next, see, from the symbol, we have this a bypass symbol for the BFD. Next, let's go to the model motor. Okay? Double click this. Okay. For performing the static motor starting analysis, we're going to update only the part which is in the load. Okay, from this, click this. Okay, and we have here acceleration time, static starting. Okay, so from the value of no load, for example, let's provide 2 seconds. And for the full load, let's provide here 4 seconds. Then, let's click OK. Then, from the uppermost of our screen, we have here the fifth icon, the motor acceleration. Let's click this one. Then, the next thing that we're going to do right now is to go to the study case of this motor starting analysis. Let's click OK on this. Okay. So we have here, first we're going to provide information on the event section of the motor starting study case. So here we're going to assign the total simulation time, okay, for this study case, let's say 10 seconds. Okay. And then we're going to create an event. Okay. We add here, from this event, we add, click the add. Let's click the add. Okay. And here, let's say the event ID is, this is motor 1, start. Okay. Let's see, start. Meaning, we'll provided here 1 second. Okay. Meaning, when we're going to perform the motor starting analysis, the motor will start after 1 second. So let's click OK on this. Okay. So from here, action by element, we provide here the information add. Okay. Click this add. So we have here element type motor. This is okay. Action start. Now we're going to select which motor that we're going to model from here. Okay. So from here, we're going to use that motor which is connected in bus A. Okay. Click this one. Okay. And let's click OK. So, no, this motor is for 500 kilowatt, 6 kV. Okay, let's update this, edit this one. Okay. And this motor. Okay. Let's click this and let's click OK. Okay, so we have now here the 8,500 kilowatt motor, 33 kV. Okay. Okay, so let's from here we're okay from here now. So let's click OK on this button. Okay. Now we're going to come back because we're going to come back on the study case because we have updated only the event. Okay. We'll go to the alert button here. Here we have the default from ETAP, and let's check what are the parameter, what are this default value. Okay, for the starting motor, the terminal voltage, the critical will be 80%. This is fine, and the marginal is 90%. Okay, for the bus voltage, okay, This is the bus voltage for the wherein the motor is connected. Okay. So the critical one is 80% and the marginal is 90%. This is also okay because right now our motor this is normally being assigned for the bus bar motor 80%. Okay. But for the bus, for the grid bus, here 92% for the critical and 95% because this is upstream. It requires that during the starting of motor, the percentage has to be more than 90%. So that's why we have here 92 for the critical and 95% for the marginal. So we're not going to change this one. This will okay. Okay. For the buses which is greater than or equal to 10 kV, we have here 90% and 95%. Okay, this is also okay. For the buses, okay, between 1 kV to 10 kV, so we have 6 kV here. Also, our setting here for critical is 90% and for marginal is 95%. For the buses which is equal to 1 kV or less than, since we have 400 volts here, the same, we have here for the critical is 90% and the marginal is 95%. So here, we're going to adopt what is the default provided by ETAP. Okay, from here, let's click OK. Okay, so before starting, we have here two icons here. The first one is dynamic motor starting, run dynamic motor starting. And the second one, the run static motor starting. So we'll be using the second icon. But before that, let's click this icon here, the display options. Okay. From the display option on the bus bar later, after we perform the motor starting analysis, we should change this one by percent. So that we can check because our alert is by percent, right? So it's better also that we assign by percent. So the bus magnitude and also the load terminal magnitude. Okay. So let's click OK on this one also. Okay. And now, I think the system now is ready to run for motor starting analysis static. Okay. This icon, run static motor starting. Let's click this. Okay. So we have here the motor starting time slider. Okay, let's move this one upper. Okay. And we have here the motor starting analysis alert view. Okay. So let's move also this one. Okay. And let's expand this and check what are these alerts. Okay. Okay. Here we have only one marginal on the 132 kV substation. Okay. Since our marginal is set into 92%, now it's operating at 90.6%. Okay. From here, see, here, if you check the operating percentage from here, the buses, our settings for all the buses, the voltage should not drop below 90% of the nominal voltage. But here, if you can check it from here, I think all of the buses are operating below 90% against the nominal voltage. So that's why we have here a lot of buses here under critical under critical value. Okay, so this information, this can be checked also from our this report manager here. If we click this, we have this information. Okay, this critical alert report. See, the condition, all are under voltage. From 33 kV bus, 132 kV bus, all this 32 kV bus here, 6 kV, okay, also down the 400 volt bus, okay. Okay, so there was a serious issue when running an 8,500 kilowatt motor without the variable frequency drive. Imagine here, percent operating 79.6. Okay, this is also in critical value, 90. We have here 80, 88.8, 79.9, 88.7. It doesn't reach on what is on 90% of the nominal voltage. That's why huge. It seems all of the buses are in critical value. Okay, so here, we have here the motor starting time slider. So what's the purpose for this one? Okay, let's go to the alert view. From the duration, okay, we have here the duration of 3.98, everything. Okay, meaning this motor, the starting duration of the motor is 3.98 seconds. Okay, we have set this one that the motor will begin at 1 second, meaning at after 5 seconds, that's the only the time that the motor, or 4.98 seconds, that the motor reach its speed. Okay, so let's close this motor starting analysis alert view. Okay, let's go to this motor starting time slider and let's check. Okay, so we have here the this is at time 0 before the start of the motor, and this is our percentage of our bus voltage. Okay, so from here, let's go to around 1 point. Okay, this is 1.68 seconds, meaning our motor is already start running. Okay, so see, the buses for this 33 kV bus wherein our motor is connected at the time of 1.6 seconds, it means after 0.68 seconds, when the motor starts, the bus voltage is 80.17 here. And the other nearby buses, see, okay, here in the 6 kV, okay, we have 79.7%. Up here, for the grid, we have 90.55% of the nominal voltage. See, imagine here, it's very low for the 33 kV switchgear. We have only 79.98% against the nominal voltage. Okay, downstream, the same, 79.88%. And this one is 86%. Okay, we have very serious issue, running a very huge motor. See, imagine an 8,500 kilowatt motor running on the system without connected as a direct online, without any BFDs, without any soft starter to limit the starting current. Okay, so I will show you also to you by clicking this motor starting plots. Okay, let's click this icon. Okay, just hold on. Okay, we have here. Let's go into select the motor. Okay, and this is the motor that our model motor. The plot type will going to check the current, okay, and also the voltage, terminal voltage, okay, of the motor, and the voltage at the bus, okay. And let's plot from here. Let's click this plot from here, okay. Okay, so this is the characteristic of our current. Our study case, we set that the motor has to start at 1 second. Okay? At after 1 second. Okay? So from here, okay, during starting, okay, the current reaches around almost 5 times of the full load amperes. Okay? For the period of around, since our duration for the starting is 3.98 seconds. So, around 4 seconds, the motor achieve the rated speed at around 3.98 seconds. So, from here, after that one, almost 5 seconds, okay, the motor now running its normal speed with the rated full load amperes. Okay, this is for the current. Okay, this side here, this is for the motor base. Okay, for the motor base, okay, from here, during the starting, okay, and during the starting period from here, okay, the terminal voltage is around 80%. And after reaching the speed, okay, after 5 seconds, now the motor is at almost 100 or around 100% of the terminal voltage. Okay, this is the characteristic for the voltage at the motor terminal. Okay, here this is also the characteristic of the voltage, okay, on the bus. Okay, see, imagine from here, before the start, the bus voltage is 100%. During the start, the bus voltage reaches below 80% in 4 seconds. And get back, but not in 100% anymore. It's less than 100% after 4.98 or after almost 5 seconds. Okay, let's go back to our single line diagram from here. Okay, what if, okay, so this is the reason why we provided this project, we provided the variable frequency drive in order to resolve the issues on the voltage dip of all the buses. Okay, so we have here, what are the benefits for this variable frequency drive? Okay, these are controlled, this can control the starting current, okay, reduce power line disturbances, lower power demand on start, controlled acceleration, adjustable operating speed, adjustable torque limit, controlled stopping, and also it provides energy savings. Okay, so those are the benefits of the variable frequency drive, having the variable frequency drive. Okay, what if we connected if we have the BFD of this motor? Okay, let's perform the simulation, removing the bypass from here. Okay, let's double click this rating. Let's remove the bypass. Okay, now this motor, okay, is connected now with the variable frequency drive. Let's see what happened when we're going to perform motor starting analysis. Okay, let's click this icon from here, run static motor starting. Okay. Okay, we have an error here saying at the BFD1, a motor is started by the BFD. The starting motor with such a BFD cannot be actually simulated in static motor starting calculations. Okay, so please run dynamic motor starting instead. Okay, let's go to the single line diagram. Okay, so that's the so meaning it's not possible that, of course, the philosophy of having that's the reason why we need to run motor starting without BFD, because there's no use of running a motor starting when we have the BFD, because the BFD control the starting current. Yes, control the starting current. Okay. In our next lesson, okay, we're going to perform this dynamic motor starting and compare the difference between dynamic motor starting and static motor starting. Okay, thanks for watching.